Testing. We should be, I believe. Oh, shoot. No, never mind. We should be okay. Did I get the number wrong? Oops, got the number wrong. Edit video. We should be live. And we're just going to give it a few minutes before we get started. Because we want to let people stream in, you know. Welcome, welcome. Howdy, howdy. Here's the paper that we're reviewing today. We will be starting in just a mo. Just gotta let some people stream in as we get started. Did I go to MIT? No. Super quiet? How's that? Is that better? I do mind. I'm not going to tell you where I went. That is for me to know and for you to not know. Welcome, welcome. Howdy, everybody. We're going to be getting started in just a mo. Letting some people stream in. You know, we can get more people in here. How is the audio okay? Is the audio volume all right? Checking on YouTube and on TikTok. Okay, so audio seems fine on TikTok. Cool. For those watching on YouTube, how is it? How's the audio? Anything? No? Well, we'll be starting in a few minutes anyway. Okay, audio's good? Great. Then we can just start. We're going to give it another minute or two while people stream in and, you know, get situated, and then we'll start. Great. Glad to hear it. Audio's still very quiet. Maybe you just have to turn up the volume, Dweep. Because it seems like that's a you problem. My audio seems to be like it even clips a little bit. So that is a you problem. Okay, well, why not we get started then? So, right. So today we're talking about dark matter, or we're talking about gravity and how we might solve the dark matter problem. Oh, let me move. Actually, can I just do, if I move this, does it change anything? Okay, good. Might solve, yeah, so they're going to try to solve the gravity problem. Who knows if they're going to succeed. What they're talking about is energy momentum squared gravity. So this is an alternative model to gravity. If you want to watch on TikTok or on YouTube, probably watching on YouTube is in principle better, but it's up to you. So they're going to study a modified version of gravity and see if it can explain dark matter. So let's read the, oh, by the way, the authors are H.R. Fazlollahi, H. Velten, and H. Shojaie. I don't know where they are. I guess they're in Brazil, Iran. So let's see. Right, so let's start with the abstract. In this study, we examined the energy momentum squared modified theory of gravity, where the squared term, T mu nu, I will explain this later, is incorporated into the conventional gravitational Lagrangian. This modification aims to account for dark matter effects on galactic scales. Specifically, we analyzed the model near general relativity solutions for spherically symmetric and static metrics. By fixing the components using the rotational velocities of galaxies, the model demonstrates the emergence of flat rotation curves in the galactic halo. Additionally, we investigate the proposed model's predictions for the light deflection angle and radar echo delay. By the way, if you want to follow along, just type in ARXIV:2501.19141V1 into Google and you will find it. It's freely available. You can read it yourself. Hold on, I'm just getting... Right, so let's get started. Yeah, the number is, it's on the side here, ARXIV 2501.19141. You need to change the title on the video on the live. Is there something wrong with the video with the title on the video on the live? Let me just double check that. Make sure that nothing's going funky. It should be fine. What's wrong with the, Oh, yeah, I didn't... Oops. The description's right. Yeah, let me just fix that really quick. The description's right, the title's wrong. All right, should be fixed. It's the title on the live on YouTube. So if you're watching from TikTok, it doesn't affect you at all. Right, okay, let's get started. So like most physics papers, they're going to start with an introduction and kind of lay out the problem that they're trying to solve. This is standard fare. One of the enduring puzzles in modern cosmology concerns the dark sector, encompassing dark matter and dark energy. The investigation of galactic rotation curves meaning the speed at which something rotates around the galaxy in its orbit, as a function of how far away it is from the center. So the investigation of galactic rotation curves and the mass discrepancies in galaxy clusters, so we see more gravity in galaxy clusters than you'd expect, led to the discovery of dark matter, which constitutes approximately 27% of the matter-energy content of the universe. Conversely, the current accelerated expansion of the universe is attributed to dark energy, which accounts for about 68% of the universe. Various proposals have been made to explain the dark sector. In order to keep agreement with observations and rely on the fundamental properties derived from particle physics and quantum mechanics, two notable dark energy models are the agiographic, or I've never heard of this, the agiographic and holographic scenarios, which are based on the quantum properties of spacetime or the entropy of black holes. Okay, never heard of that before, but okay. Axions. Okay, so this was definitely not written by an English first language person, because there's some weird grammars, but that's okay. This is a preprint. It's not been published yet. Axion-like particles are, for example, interesting candidates, being a non-baryonic field proposed to account for dark matter properties. So an axion is just a type of particle, and the point is that if those things exist, then they could potentially be the kind of things the kind of particles that would be necessary to explain dark matter. So axions are a cool candidate. Another prominent theory involves weakly interacting massive particles, WIMPs. So these are just particles that don't interact with anything except via the weak nuclear force and gravity. So another prominent theory involves weakly interacting massive particles, a broad class of hypothesized particles that could contribute to dark matter. Heavy neutrinos have also been considered as potential dark matter candidates. Heavy neutrinos are kind of, as the name implies, they're neutrinos, but they're heavy. Neutrinos are already kind of weakly interacting particles, but they're very, very light. They're not massive particles. So if there were heavy neutrinos, then it's possible that they could account for dark matter. Despite these theoretical developments, both direct and indirect searches or accelerator experiments have not provided conclusive evidence for these particle-based scenarios. So this is the idea that this is like a problem, right? So we have this reason to believe that there's something that we call dark matter, which explains why we see these anomalies in the gravitational observations that we make. But it doesn't seem like we've detected, or it doesn't seem like the thing that causes those anomalies is a particle, because we haven't found the particle. And maybe we just haven't found it yet. Maybe it is a particle, but it at least should make you think. Consequently, attention has shifted towards modified theories of gravity as an alternative approach to the particle dark matter paradigm. These theories incorporate additional terms into the standard Einstein-Hilbert action. The Einstein-Hilbert action is just one way of formulating general relativity. So these theories incorporate additional terms into the standard Einstein-Hilbert action, allowing dark matter to be interpreted as a geometric or matter-related evolution in spherically symmetric and static spacetime. So they're saying if you modify general relativity enough, then maybe you can eliminate the need for dark matter. By the way, neutrinos don't interact at all with electromagnetism. Similarly, dark energy can be modeled either as a result of purely geometric evolution or as a coupling between space-time and matter in these modified gravity frameworks. Some theories also propose dark energy as non-Einsteinian matter fields, or an effect of interior matter evolution. Interior matter evolution, I believe that's referring to the timescape stuff that was recent. As such, modified theories of gravity offer powerful tools to unify the explanations of dark matter and dark energy within a single theoretical framework. So this would be a very successful thing. If you can do this, if you can write down a single equation that doesn't have any additional particles or fields and isn't ad hoc, but it can explain both dark energy and dark matter, then that's a win, right? So in this study, we examined spherically symmetric and static spacetime. So spherically symmetric is as the name sounds. It's spherically symmetric. If you rotate it any which way, it doesn't change. And static just means that it's not changing in time. So we examined spherically symmetric and static spacetimes to explore dark matter as an effect of a recently proposed modified theory, energy momentum squared gravity. So they're going to basically take, and they'll go into the details of what it is in a minute. It's just a modification. This theory extends the Einstein-Hilbert action by incorporating the additional term T mu nu, T mu nu. So T mu nu, this T with the subscript mu nu, that's the Greek letter mu, Greek letter nu, that basically tells you the energy and the momentum and the pressure. It tells you stuff about what's happening. It tells you about how the matter is distributed, how the matter and energy is distributed. And so instead of just having one of these, this is the stress energy tensor, they're squaring it. So you have two of them showing up. The term depends on the source matter field and introduces a nonlinear density and pressure contribution to the field equations. As discussed in reference 35, this alternative theory of gravity predicts a non-singular universe. That's interesting because it means that you don't get, presumably, you don't get like a singularity at the black hole, a singularity a singularity at the Big Bang, or singularities in black holes. Furthermore, during the matter-dominated era, so that was when dark matter was, or when dark energy was weak, the dominant force in the universe was gravitational attraction. So that's what they mean by matter-dominated era. Furthermore, during the matter-dominated era, and given the small values of the theory's coupling constant, alpha, the deviations from the standard lambda CDM model are negligible. So lambda CDM, that's just like your normal Big Bang model that has a cosmological constant for dark energy and just has invisible matter for dark matter. This makes it compelling to investigate whether these additional terms can account for observations in galactic halos, eliminating the need to invoke mysterious masses as dark matter. So, and now they're just going to tell us about how it's organized. So let's just quickly go over that. The paper is organized as follows. Section 2 provides a review of energy momentum squared gravity. That'll be helpful for y'all. In Section 3, we examine the field equations for spherically symmetric and static isolated systems in the vicinity of general relativity. They're just telling, we'll go over what this means when we get there. Section 4 explores the propagation of light within the typical galactic framework. Finally, the final remarks are presented in Section 5. Okay, great. Throughout this work, we will adopt the geometrical unit system where the speed of light, c, is 1, while reducing Planck's mass as the square of Planck's mass is kappa to the minus 1. So all they're doing is they're just using a set of units that make the calculations a little easier. So let's move on to Section 2. Any questions, or should we just jump right in? No, it does not correspond to wavelength and frequency. All right, let's do it. So Section 2, energy momentum squared gravity review. I don't actually know anything about energy momentum gravity. Hey, Quantanaut from JLab. I don't actually know anything about energy momentum squared gravity, but I can kind of guess what it'll be. So let's just review. In this section, as a first step, we revisit energy momentum squared gravity to derive the field equations. We also apply it to the static and spherically symmetric spacetime in order to explore the basic correspondences between the metric functions and the source terms. So for those who don't know, the way that general relativity works is essentially you have a relationship between the matter and the matter and the spacetime curvature. And the spacetime curvature is described by something called the metric tensor. And the metric tensor tells you how distances change with position, how durations change with position. Essentially, when we say spacetime warps, what that means is that the way that you measure distances, the way that you measure durations, those things are those are things that are changing. And so literally rulers get longer and shorter, clocks tick longer, tick shorter. These are things that literally happen, like measurably happen. And so when they say that they're going to explore the basic correspondences between the metric functions and the source terms, what they're saying is that the metric, and the metric is described mathematically, the metric is going to depend on the source of the curvature of spacetime, on the matter. And so that's the thing that they're going to be talking about. Is this one f of RT gravity theories? I'm not sure if it is. Well, okay, yes, I suppose in principle it is because it has a t term, but we'll see. So the action for this alternative theory is expressed as this. Now remember, an action is just a quantity that essentially characterizes the trajectory, in this case, the kind of the evolution of spacetime, for any physical system that doesn't have friction, basically. And so one of the easier ways to derive physical laws is to write down an action, and then you can do something called variation to that action, and you can get out physical equations that tell you how things should be related to other things. So the action here, we have 1 over 2 kappa. That's just a constant that we don't have to worry about. We have this, this term here. If you've taken calculus, that's essentially your Jacobian in 4 dimensions. You have this r. The r here is the Ricci scalar, which essentially tells you how the volume of spheres relates to their radii. So when the Ricci scalar is 0, the volume of a sphere is 4/3 pi r cubed, where r is the radius. When the Ricci scalar is not 0, when it's positive or when it's negative, that formula changes. And then they have this extra term here, alpha t mu nu, t mu nu. So they're adding this extra term that isn't usually there to modify their Einstein gravity. The Einstein gravity usually just has this Ricci scalar here. And then they have the matter component. So this tells you how the matter will evolve. Don't worry too much about this. Nothing new is happening here. So here they're telling us that g, r, and alpha respectively refer to the determinant of the metric g mu nu. So again, it's the determinant of the Jacobian, really. I mean, it's the determinant of the metric, but the Jacobian shows up there if you wanted to change coordinates. Then you have r, capital R, the Ricci scalar, and then you have the gravitational coupling constant of the modified gravity sector. So this alpha here essentially just controls how influential this modification of gravity is. The extra term should be on the matter part, not the geometric term. Could be. I mean, usually L is determined. Usually L is like, you know, phi squared or like a phi to the 4th theory or something like that. This is not that. So, but it doesn't matter where they put it, right? It really doesn't matter. The LM denotes the Lagrangian density related to the energy momentum tensor. So T mu nu is explicitly given by this formula. Now this is horrible, but this delta, this is kind of like a derivative. So you know how you have d divided by dx when you take a derivative? This is like a derivative, except it's with respect to a function. The function here being this metric tensor. And you're just varying, or you're taking the derivative of the Lagrangian density. And so this actually gives you a formula for T mu nu. That's the important part. The variation of the action with respect to the inverse of the metric tensor g mu nu obtains the field equations. So you get these field equations. Now, importantly, when you vary the Ricci scalar, and you have to also vary the determinant of the metric, you get the left-hand side here. It's the Ricci tensor. It's an r, but now it has a subscript mu nu. And then there's you subtract off some amount of the Ricci scalar times the metric. Remember, g, the metric that tells you how you measure distances and durations. So this is just a particular combination of geometric things. This tells you how the volumes of sphere changes. The Ricci tensor tells you something about how the volume, or how the it tells you something about how the cap of a cone. So imagine that you have a point and you shoot a cone out in a direction. It tells you how the area of the cap of that cone changes with both angle that you shoot it out at and the radius. So it's just another geometric feature. And then we have kappa times this TE. Now this is an effective energy momentum tensor, which is essentially just, it's how they're going to capture the, it's not like the actual energy momentum tensor. It's not this thing that tells you just about the matter, but it tells you how the energy momentum tensor would have been if this extra term wasn't there. So they give a formula for the effective energy momentum tensor, and it's derived from varying this formula up here for the action. And it's horrible and messy, but here's the result that they get. So it is the normal energy momentum tensor, and then it has a whole bunch of extra stuff. And that whole bunch of extra stuff is going to be related to alpha, right? If alpha is 0, that tells you how much, alpha tells you how modified your theory of gravity is. So if alpha is 0, it's just normal Einstein gravity. So this thing, this effective energy momentum tensor, should just be the energy momentum tensor when alpha is 0, which is true. In this case, if alpha is 0, all of these terms go away. But if alpha is not 0, then you get a whole bunch of extra stuff. In particular, you get a term that looks like the energy momentum tensor squared times the metric. You get some amount of the Lagrangian matter density times the energy momentum tensor, or a trace-corrected version of the energy momentum tensor. You have more terms that involve the energy momentum tensor. T here is the trace. So the energy momentum tensor, a tensor is like a matrix. So the trace of a matrix is just the sum along the diagonals of that matrix. So you're multiplying the sum along the diagonals times the original energy momentum tensor. And then there's just a whole bunch of extra terms. There's this extra horrible term as well that involves taking two derivatives of the Lagrangian density, the matter Lagrangian density with respect to the metric. It's just a horrible thing. But the point is now we have a set of equations. These are the modified Einstein equations. We have the Einstein tensor, that's what this thing on the left is called. And then we have something that behaves like an energy momentum tensor, just modified. So they now say with this strategy, the field equation 3, that's the field equation, resembles the GR structure in the sense that it keeps all T mu nu dependence in the right-hand side of the field equation. So they could have put this stuff on the left-hand side of the equation, but that's a choice. And if you don't do that, then it looks just like general relativity. This is an equation that looks like general relativity. If that E wasn't there, it would be general relativity. Anyway, now we can proceed. So now they're going to actually give us a specific form for what the energy momentum tensor is. So by considering the energy momentum tensor assumes the perfect fluid form. So a perfect fluid is just a particular type of fluid. Essentially it has, what is it? It's like a non-interacting fluid, and it has a pressure and an energy it has a pressure and a velocity that's related in a particular way. Essentially the energy momentum tensor is telling us that it has a certain amount of pressure. This is the pressure. And then the kind of the energy and the momentum part of the stress energy. So the energy of the gas is sort of related to its temperature perhaps, and its pressure show up in the energy momentum tensor here, where U is a velocity. So like you can imagine a whole bunch of gas that's just all moving in one direction. That would be an example of or rather a whole bunch of like fluid perhaps all moving in one direction. That would be an example of a perfect fluid. So this is just a canonical form. It's a very simple way of describing it's a very simple energy momentum tensor, and it's a good model for a lot of things. So that's why they're studying it here. Anyway, so we have rho, this Greek letter rho. Rho is the energy density, P is the pressure, and U, mu, is the co-moving forward velocity satisfying these conditions. So it's just a velocity vector. So once you do that, once you set that, we obtain the following. So you can take the trace. Taking the trace, you get that it's 3 times the pressure minus the energy, fine. And the square is the energy squared plus 3 times the pressure squared. I mean, it's just what happens if you square this thing, right? Now, by taking the Lagrangian to be negative of the energy density, now why might you do that? Yeah, why might you do that? Interesting choice. You'd think that you would want to. Oh no, of course. That's yeah. This is just a convention. It's because they have a -1 here. So if you take the Lagrangian to be negative the energy density, and using relations 6 and 4, so you use these relationships and you use that relationship and plug it in here, the modified Einstein field equations become, they become this horrible thing. It's not great, but let's just stare at it for a little bit. So we have the left-hand side hasn't changed. All we've done is we've moved an index from being down to up. And when you move an index, so this is the thing that we started with. When you move an index up on a G, it becomes a delta. It becomes the identity operator. So it's just a matrix with all ones along the diagonal. And so that's what we have here. All we've done is move an index up. And then they've just plugged in what they have before. So we have, this is the old result. Oh, that's a typo. This should be U mu, U nu, right? So this is the normal energy momentum tensor, and then here's all the corrections. So the corrections look like some amount times the identity, and it's just a whole bunch of other stuff. And in particular, you have a derivative with respect to the metric of the energy density. Fine. The right-hand side reveals that we are no longer dealing with a standard perfect fluid, but rather with an effective fluid. So we have your standard perfect fluid, and then you have a modification. So it's an effective fluid. The cosmological applications of this theory have been explored across various dark energy scenarios. Cool. Additionally, studies in recent years have considered gravastars and compact stars within the framework of this theory. Also cool. In this work, however, we employ this alternative theory to investigate dark matter in an isolated system described by a static, spherically symmetric metric. Now, let's talk about the static spherically symmetric metric. So when we say it's spherically symmetric, what that means is that there should be no dependence on angles. So it should, the only thing that the metric should depend on is how far away you are from, from the center of your coordinates, wherever your mass is. And when it's static, that means that it shouldn't depend on time at all. So if we write down the standard metric, what that means is that this part here, so this part, you can just think of it as a tiny little contribution to the surface area of a sphere, right? So this encodes all of the spherical symmetry here. And then it says the way that you measure radial distances, so distances away from the center, that's going to be different. They're just going to specify that it's the exponential of some function of distance. So it depends on how far away you are. That's how long rulers are in the radial direction. Similarly, the length of clocks, or the duration between ticks of a clock, also depend on how far away you are from the center. And that's what this term here refers to. To maintain simplicity, tough stuff, the effective energy momentum tensor of the matter is modeled as a pressureless fluid. So they're going to assume that the pressure is 0, where the matter Lagrangian is equal to pressure is assumed to depend, that should be a rho. That should be a negative rho, actually. Is assumed to depend solely on the metric components without their derivatives. Consequently, the various components of the field equations can be expressed as follows. So now they're just going to use this fact. They're just going to use the fact that, yeah, this should be Lm equals negative rho. I don't know why they have that there. Yeah, I think that's just a typo. Because, yeah, there's no p's popping. Yes, that's just a typo. It's fine. Yeah, and they're also assuming, by the way, that this term vanishes, that there's no dependence on the derivatives of the metric tensor. Sorry, this term won't vanish, but hold on. Yeah, that term shouldn't vanish, but we'll see what they say. Anyway, let's keep going. Consequently, the various components of the field equations can be expressed as follows. So we have this field equation. They're going to lump everything on the left-hand side to be G. That's typically what it's called. It's called the Einstein tensor. So we have the TT component. So now we're replacing mu with T and nu with T. So, and then we're going to plug in a T for all of the mu's and nu's on the right-hand side as well. And it simplifies to this expression. And by the way, we also now know what the metric tensor is. Sorry, what the, yeah, we know what the, that's a typo as well. That should be a mu nu. We also know what the metric tensor is. This is the metric tensor. So there's going to be stuff that shows up that depends on A of R, and it's going to depend on B of R. These are just two arbitrary functions that they're going to try to solve for. So we have that the Einstein tensor depends, it goes as, and this is just by calculating the left-hand side, by the way. You can calculate the curvatures by using this metric tensor. So that's what's on the left-hand side here, over here. So the left-hand side, this curvature term, it goes as 1 over r squared times e to the b minus b prime, where b is the derivative with respect to r, divided by r times e to the b minus 1 over r squared. Fine, that's the curvature. And then on the right-hand side, we have all this matter stuff. So we get the normal matter term, which is minus k rho, kappa rho. And then there's one extra term that comes from the failure of this thing to be the Einstein-Hilbert action. Rather, it's the modified Einstein-Hilbert action. That's why there's an alpha here. Remember, alpha controls how different from typical general relativity you are. And so there's this term that depends on the energy density squared, hence the name energy momentum squared gravity. And then we can do the same thing for the radial component, and we get that you have a curvature term, fine. But in this case, for a pressureless fluid, usually this would be 0. However, because we have energy momentum squared here, this is actually going to depend on the energy squared again. And then we can do the same thing for the angular components of the Einstein tensor. Again, we get some curvature bits. And then we get, again, something that would have normally been 0, but it isn't because, again, we have an energy momentum squared. And so one way that you can see this popping up, by the way, is you can see this popping up in terms like here, for example. You would expect that when you square this, u mu, or when you square, sorry, I need to make sure that I'm getting this right. Let's take a look at GRR. So if we have we don't want to trace this, we want to take GRR. So we need the R component of the velocity. Oh, maybe they'll explain. Let's just keep reading. But essentially what's happening is that we're picking up on terms that oh, here it is. It's because of these terms. So like if you put RR here, you'll get a rho. You'll get a term that depends on rho. And then you'll also get the similar things that happen here. I mean, here's another one. This is actually a typo here. There should be a, let's just double check. Where's the mistake? T mu nu. Yeah, there's a mistake here. It just doesn't have the right tensor structure. My guess is that there's supposed to be a delta mu nu there, but that's okay. I'm going to trust that they got these correct because these are the kinds of things that they would have done this on a computer and then they just probably copied it incorrectly. This they would have double checked. So we'll trust this is correct. We could verify it if we wanted to, but I'm not going to. Anyway, so as shown, in the absence of pressure, the energy momentum squared term introduces equal radial and tangential pressures into the model. So essentially what's happening is that even though the actual fluid doesn't have any pressure, the effective pressure that the curvature sees, because curvature typically sees pressure, is there is an effective pressure there, which is interesting. It adds a pressure in all of the directions, even though the fluid is pressureless. And this is proportional to the square of the matter density rho squared. Due to the presence of rho squared in equations 9 through 11, that's these, obtaining exact solutions for the metric components in expression 8 is not straightforward. So yeah, I guess they're saying that actually solving this is very, very hard. Basically, you have 3 equations here. These are equations that tell you about B, it tells you about A. And those are the things that you're trying to solve for. You're trying to solve for A and B, but it's hard, is what it seems like what they're saying. To address this, one can eliminate rho squared by subtracting equation 10 from equation 9. So you take this, you subtract off that, okay. And then you get this. Ah, that's a nice formula. You get this very, very nice formula. This relation provides a linear combination of the derivatives of the metric functions in terms of both the first and second powers of the density rho. It proves useful in the following section for determining the exact forms of A, B, and rho. So they're basically going to use this result to then go solve the system in more detail. All right, any questions so far before we move on? This is kind of like a public peer review. It's not an official peer review. This is not going in a journal right now. I wasn't asked to review this. I just thought that it was an interesting paper and I wanted to go over it with y'all. By the way, if you're watching on TikTok or YouTube, make sure to like the live. It's a cool thing to do. Oh, I was just called Unk. Awful. All right, well, let's continue. So we're going to talk about section 3. Can I show that again? Show what again? Anyway, let's talk about section 3. To determine the set of functions a, b, and rho in this model, those are the variables here. Those are the things we're trying to find. It is essential to establish a relationship between the time and radial components. Fine. Oh, 10 and 11. Yeah, I can show that. 10 and 11 are these 2 equations. So all they're doing is they're just subtracting equation 10 from equation 11. So notice importantly that they're subtracting equation 10 from equation 9. So they both have a 1 over r squared term, and they both have a 1 over r squared e to the beta or e to the b term. So you just end up with these 2 terms. You have this term minus this term, and then you just subtract the right-hand side. So it simplifies the situation a little bit. You end up with this one. Anyway, let's continue. All right, To determine the set of functions a, b, and rho, in this model, it is essential to establish a relationship between the time and radial components. Due to the influence of the matter field, deviations in space-time around a central massive object are expected. Yes. One expects deviations when you have matter. Absolutely. In this context, if the combination of a prime plus b prime forms a well-defined differential expression, a solution of the form e to the a of r plus b of r equals L of r can be obtained as in 42. In this proposal, one expects the function L of r to be slightly different from 1. Okay. As a plausible form, we assume this. Okay. By the way, if you're just joining us, the paper that we're reading is entitled Dark Matter and Energy Momentum Squared Gravity. And the paper, if you want to follow along, is ARXIV. You can type this into Google, ARXIV : 2501.19141, and you'll find it. And if you missed the beginning, feel free to go back and rewatch it on YouTube. It will be. It is currently live streamed on YouTube, and you can go watch from the beginning if you'd like. Right. So they're just going to assume that e to the a plus b is equal to some function L of r, and they're just going to assume that's slightly different from 1. And so as a plausible form, this is called an ansatz. They're going to suppose that this is what L of r is equal to. So they're just kind of giving an ansatz for what a is, where s here is a dimensionless parameter, and sigma is the length scale of the system. It's like the size of the thing. To remain in the vicinity of general relativity, it's necessary to have that s is much less than 1. This way you get that L of r is approximately 1 plus s times the log of r over sigma. Now, why are they allowed to do that? This is the question. Deviations in spacetime around the central massive object are expected. Sure. So if you have a central massive object and then you have fluid around it, obviously you would expect deviations in spacetime, even in general relativity. So my question is, I see. Okay, so in general relativity, if they were solving this in standard general relativity, a of r plus b of r, or the exponential of a of r. Oh, actually no, those don't cancel. Yeah, let's keep reading, see if they can explain this better. So if this is the case, then one obtains this: a prime plus b prime equals s over r, where s is just some dimensionless parameter. And so essentially what they're doing is you're subtracting off 1 from. You can expand this, and you get you can do a Taylor series expansion here, and you can match it, and you can get a formula for a plus b, or a prime plus b prime. Which is kind of what we want, right? That's kind of what we were working with. Plugging the above relation into 12 and using 13 gives metric components as a function of density. So now, so if you know what a prime plus b prime is, you can plug that into 12, and then you can just solve for a, b, and rho. Now you've done the work. So you get e to the b is this thing where s is just some small number, and you have that your metric component depends on your density and on the distance. And then you get that e to the a, which is the other metric component that we needed, also depends on the energy density. It depends on the distance. It goes to the distance squared in this case. And it has this extra factor of r over sigma to the s. Fine. What's weird is that this number is huge. This number is like enormously large because s is supposed to be very, very small. So we'll see what we have to make of this. And by the way, this number is small because, again, s is supposed to be very, very small. So this leads to the following set of relationships. So once we have this, then we can plug those back in. Do we have a relationship on rho prime? Where are they getting the relationship for rho prime? That's what I want to know. So we have r here. We have rho here. Where is that rho prime coming from? I see. So if you take the derivative, if you know what a and b are, you can differentiate that. And you can differentiate this whole thing. Actually, no, that's not what they're doing. Yeah, that's not super clear. Where are they getting these? Where are they getting this relationship here? Let's look. So this is equation 19, which I think that, yeah, this is equation 9. They've plugged it, yeah, okay, they've plugged in equation 9 here. And so what do we have here? We have 1 over r squared e to the b. So they have a, let's check. So we have the minus 1 over r squared. Okay, that's correct. Minus 1 over r squared. Fine, we have that here. And you can differentiate this. But if you differentiate that, yes, if you differentiate this, if you differentiate e to the b, good point. If you differentiate e to the b, then you'll get a b prime over, or you'll get a b prime times e to the b. Of course. And we know what e to the b is. It depends on rho. So if you differentiate this, you're going to get rho dependence. You're going to get derivatives of the density. And so that's where we're getting the derivatives of the density here. So we get these 3 equations. These are the equations that we get from plugging in e to the b and e to the a into these equations. And also differentiating so that we can extract out the b prime and the a prime. And then I guess the a double prime as well. So, horrible stuff, but it must be done. Such is the way of things, right? So by eliminating rho squared from the left-hand side of equation 19, so we have a, where's a rho squared? We have a rho squared here, we have a rho there and a rho there. So you can eliminate that. I guess we have, yeah, just by moving it over to the other side. We arrive at, oh, actually, what are they doing? Are they eliminating it by using another equation? They might be. So you arrive at this equation by eliminating, okay, so they're just solving for rho squared from this equation, and then they're plugging it back into these equations, presumably. Yeah, it's interesting. Which one are they getting? Because now they have 1 equation instead of 2. Well, it must be this equation that they're using. They must be eliminating rho squared from this equation and plugging that back into equation 21. Because they have a rho double prime here. And so, yeah, I think that they're just solving for rho double prime here. Or they're just solving for rho squared in this equation and then substituting it back in here. That's my guess anyway. But we can just go compare with what they have. Do they have any? Yeah, so they just, oh no, but they do have a rho squared here. Why is it typical in research papers not to write the full derivations? Because it would be too long. And a lot of this stuff is expected that anybody can do. So let's think about this some more. So what are they actually doing? So they have this equation. Let's just compare some terms. I'm going to zoom out a little bit. So this term is the same as this term. This term is the same as this term. Now this term is changing. This 3r. So that term has changed, as has this term. And they have a 1 over r. Yeah, okay. So I was right. I was definitely right. So they are just solving for rho squared in this term. And then they're plugging it into this term because we have some rho squareds here. We have a rho squared here and here. And they're just plugging it in. You ever go through a level further math questions? No, generally not. Right, so we end up with this equation, which is horrible, absolutely horrible, atrocious even. The above equation allows us to obtain 2 different solutions for the density function. They're going to solve solutions. They're going to solve this equation. Okay. They absolutely used the computer to solve this, by the way. The above equation allows us to obtain 2 different solutions for the density function as a function of r. So essentially, they've eliminated all of the variables except rho, and now it no longer depends on, well, they have rho squared there. Wait a minute. If they have rho squared there, why are they? Or did they take equation 21 and plug it into equation? Regardless, they manipulated these three equations to get this equation, this horrible thing. So, and if I had Maple, I would probably just do it, but I don't have Maple right now, so it is what it is. Anyway, is there context for this? Yeah, if you go watch on YouTube, we started at the very beginning of the paper. The paper is called Dark Matter and Energy Momentum Squared Gravity. It's talking about dark matter and how we can maybe explain it with a different theory of gravity. And if you want to follow along, to read the paper yourself, type in ARXIV colon 2501.19141, and you'll get it into the and you'll find it on Google for free. Importantly, this paper is it came out like it hit the preprint server like 5 days ago. It's not even in a journal yet. It has not been peer reviewed yet, which is why we're reading it, because it's interesting. So there's still typos and stuff, but it's a preprint. Right. So we get a set of Maple is it's a computer algebra system. Yeah, it's software that you can use to simplify a lot of calculations that you might have to do. No, this has nothing to do with statistics. Right. Okay. So they read the two solutions. So you can plug this into a computer and solve it. You're going to get one equation that depends. You have a constant term out front. And then you have a term that goes as 1 over r out front of this horrible square root thing that has an r squared here and some constants, another r squared here and some constants, another r squared here and some constants. It is what it is. This whole thing better be negative. This is sussy, because this looks like it's going to be imaginary. And then the second solution is much smaller because they have to fit more stuff in, but it has a constant term out front. And then they have a whole bunch of more stuff, and it's just S's and kappas and R's and a whole bunch of numbers. Fine. Although solving equation 22 yields two distinct density profiles, when S is very, very small, both solutions converge to this. So the point is you can take the limit as S goes to 0, or rather you can do a Taylor series expansion, and you can show that they're the same up to terms that go as S. So like they just are the same, except they differ by a term that is proportional to S. And if S is very, very, very small, then they're basically the same. Well, yeah, no, that's my point. So if the numerator also has to be negative, which actually, I guess the numerator would be negative, right? So you have -4, you have -4. All these other terms go away when in the limit where S is 0. So you do get something positive out, and that's fine. Right, so investigating equation 25 shows that the density rapidly decreases with radius proportionally, with rho going as r to the -2. The density. No, but that's not true. The density is constant. I guess unless you're at 1 over, I guess, yeah, no, the density is constant though at leading order, because you're going to have a term that goes as in the small s limit. You're going to have that this term dominates, and so you're just going to have another constant out front. So this is kind of strange. I mean, I get that they differ by something that goes as 1 over r squared, but the actual density profile, either rho 1 or rho 2, that looks constant at leading order. So that's interesting that they say that. Maybe they meant to say that they're difference. No, I'm not going to send feedback. Maybe if they see the video, maybe they'll be interested. But other than that, yeah. So this is a little bit puzzling. That why they would say that. I could be missing something critical. Yeah, so I'm thinking about the limit as in small s and large r. This term approaches a constant, and this term is a constant. This guy's a little bit messier. This guy goes as what? In the small s limit, you just have this term, and then that goes as plus the square root of r. Still though, not goes as one, it doesn't go as one, they must be talking about the difference in densities. But I don't know why they're saying that. I don't know why that's relevant. It's not super useful. Taylor expansion of second and third term adds to the constant term to get 25. Right. No, that I understand. But it's just weird that they're saying that the actual density varies as 1 over r squared. Ah, okay. So in the small radius limit, when r is small, then you get 1 over r squared. Absolutely. That's probably... Is that even true? Yeah, actually, that's not even true, right? Because in this case, yeah, in the small r limit, you would only keep the... I mean, again, in the case where s is very, very small. No, I know. Well, so there's essentially two places where it could be decreasing, right? It could be the case where you're looking at the large r, like you're looking at the behavior of the density at large r, and you're saying, oh, it decreases rapidly. But here they say the density rapidly decreases with radius. So that makes me think that if they're examining near the origin, and then they're saying, oh, it does decrease quite rapidly, which is what it would do if you're near r is 0 as well. So in the small r and small s limits, then you get that their difference at least goes as 1 over r. Oh, wait a minute. Am I stupid? I'm stupid. This is not a difference. This is an equal sign. Approximately equal. Now, is that true? Is it true that in the small s limit, no, I don't think it is. I mean, let's just look at row 1, right? If we just look at row 1, you have a constant term, sure. And then in the small s limit, you can just throw away all these terms. These terms are gonna, like the denominator goes to -4, these terms go to 0, and you're just left with -4 kappa squared r squared over -4, which just becomes kappa r. So you have kappa over 6 alpha minus kappa r over 6 alpha r, which just becomes a constant. But I guess if you're keeping, you'd have to keep the first order term in s, and then I guess you could have a 1 over r squared. I guess that's fine. Ah, that's what you were saying. You were saying that the leading coefficients cancel when you do the Taylor series expansion. Okay, that I believe. Okay, so not wrong. It's actually probably right. We can actually we could verify this if we wanted to, but I don't think that we're going to. It's believable. Right. Okay. Great. This is why we do this live. Right. Using the above density in 17 and 18, so 17 and 18 is these guys. Remember, the e to the b and the e to the a, those are the guys that tell us how our space-time geometry is curved. If we now know what rho is, now we can plug that back in. And then we find that the metric functions are this horrible mess. They're just taking row 1, taking row 2, and they're just plugging in this. And you get just plugging it into these two formulas. Fine. Okay, cool. You get horrible stuff. And again, in the small s limit, we get that e to the a is 1 minus s plus s times a log, plus a whole bunch of higher order terms. And then you get that e to the b is 1 plus s plus another higher order term in s squared. Fine. Okay. So then now we know what e to the a is, we know what e to the b is. From the above solutions, one can infer that the model is flat asymptotically. The reason why they say it's flat asymptotically, actually, is that believable? Let's think about this. So certainly in the small s limit, or let's, I guess we want to look at the, we're doing a public peer review. So this paper, I wasn't asked to review this paper. I picked it because it looks interesting. So in the large R limit, that's asymptotically what they're referring to. This term goes away, and then we're left with these two, a whole bunch of other terms. And in the S, so in the case where S is small, we find that yes, okay, when S is small, this becomes 1, and this becomes 1. Fine. So it's flat asymptotically. Basically, if it's actually flat, then it should just be equal to 1. Great. To investigate whether such a model represents dark matter as an effect of the energy momentum squared term, we consider a test particle moving along a time-like geodesic orbit in the plane theta equals pi over 2. The corresponding geodesic equation for the r coordinate is given by, they're just citing, it's given by this horrible thing. It's actually really not that horrible. This is just a differential equation in the, is this radially outward? Yeah, so they're imagining, so they have the space-time geometry now. They've figured out what the space-time geometry is. And now they're going to see, okay, well, what happens if you take just like a, I don't know, an electron, and you just shoot it outward? Yeah, if you just let it be, but you specify that it's at the equator of your spherical coordinate system. And so it's either going to fall in, or maybe it'll move out, or it'll go in or out radially, depending on what its initial conditions are. If it's moving in the outward direction, then it'll move out. If it's moving in the inward direction, it'll move in. If it's not moving at all, it might fall in. But this is the equation that will tell you how its distance will vary with time. And so, and it involves a prime, it involves, yeah. Oh, actually, I'm sorry. They're actually allowing for it to move around the sphere as well. So this is, they're basically going to study an orbit. Yeah, a time-like geodesic orbit. So they're going to try to, because typically you would like to know that your gravity theory can reproduce orbits, right? So they're going to do that. So here tau denotes the affine parameter along the geodesic. Typically, in this case, it's going to be proper time. The momenta p0 and p3 associated with the test particle's motion along its geodesics in a spherically symmetric and static spacetime are conserved. So what they're saying is that here, because the Lagrangian is has rotational symmetry and time translation symmetry, we get two associated yeah, we get two conserved quantities. We get energy in particular. We have an energy conservation, and we have an angular momentum conservation. The energy here is just it's the coordinate, it's the rate of coordinate time change with respect to the proper time times this this geometric factor out front. And then the angular momentum is just kind of the rate at which it moves around times r squared. This is your standard thing. There's nothing special here. This is something that's different. It's different in this case than it would be in the normal general relativity. So E and J are respectively the energy and the phi coordinate of the angular momentum of the test particle. J is not the phi coordinate. J is angular momentum. That's a weird statement to make. They mean the angular momentum of the phi coordinate of the test particle. They just got the order wrong. Right. For motion on the stable circular orbits, i.e. when dr d tau is equal to 0. So r is the distance from the origin, and so if that distance isn't changing, i.e. dr d tau is 0, this is a derivative, so it means that the derivative, the change, is 0. That means that it would be moving in a circular path. So they're going to study circular orbits, which will simplify this equation dramatically. Then the equation, substituting in the energy and the angular momentum, so we can substitute in this guy here. That shows up somewhere in this equation. Dt d tau should show up. So this term will be 0, this term will be 0, this term will be 0. Where is this term show? Where is the energy showing up? Let's think about this for a minute. They don't need a dt d tau. So why is it showing up in the equation? Let's think. Okay, so potentially you could differentiate this thing. Yeah, but you wouldn't want to do that. That wouldn't make a whole lot of sense. I don't think it's a typo, actually. No, actually, it might be a typo. They probably need a d. Yeah. This, yeah. No, you're absolutely right. This should probably be. Yes, this term should be dt d tau. That's a typo. Good catch. Good catch, y'all. Or at least that's what they're implying. Absolutely, that it should be dt d tau. And we could probably derive that just by writing down the geodesic equation. Yeah, your geodesic equation should have dr d tau. It should have dt d tau. Yeah, this is the Christoffel symbol. This is the Christoffel term for the dt d tau term. So, yeah, okay, good catch. Right. So then we get this lovely equation. Now, E and J are both constant. And so this just tells us what A is. Now we actually already have an equation for A. Right. We already know that A it's somewhere. We had an equation for A. Well, implicitly we have an equation for A. So far away from the gravitational source as a weak field approximation, the circular orbital speed becomes this. So, yeah, okay, so they're just relating that to J. You can extract a circular orbital speed. Where am I live besides YouTube? I'm live on TikTok too. We have 273 people watching there. So you can basically calculate the speed by using this equation. With the aid of 32 and 33, so that's these two guys. The above orbital speed can be written in terms of the derivative of the metric function. Okay, seems fine. And so the speed actually, no, this doesn't come from this equation. This is just a relationship about okay, so what they're doing is they're basically doing a weak field approximation where you essentially treat it as if it's Newtonian. You can read off what the effective Newtonian potential is going to be from the metric, from the space-time metric. And then from there, you can derive what the speed should be based off of the gravitational potential balancing with the kinetic energy. And that's going to include this guy. Usually, if alpha was, A. A is the guy in front of, hold on, I just want to verify which one A is. Is A the one in front of dt squared? Where is A? Yeah, A is the one in front of dt squared. So that's the one, do live chats get saved still? I think so, yeah. So that's going to be the one in front of the dt squared, so that's fine. That's just a conversion factor between d phi and d tau, and then we just get r omega, essentially. So this is just coming from kind of treating this as Newtonian when you're far away. And so then you can combine these two equations, 32 and 33, to rewrite the orbital speed in terms of the derivative of the metric function. So that's essentially what they're doing. And so this square of the speed is the radius times this a prime divided by 2, which is interesting. Now, we have a formula for this, I think. I'm just thinking, where does the alpha actually show up? Well, they'll probably tell us. Here we are. Right. Okay, they are going to tell us. The observation of flatness in galactic rotation curves suggests that the function in the halo of galaxies is independent of the distance r. So what they're saying is that if this is going to work to eliminate our need for dark matter and galaxy rotation curves, then this v squared should be a constant, which means that a prime should go as 1 over r. This phenomenon is recognized as one of the strongest indicators of the existence of dark matter by using the density expression 25 over here. This guy, by using the density expression 25 and calculating the square of the orbital speed 35, for the very, very small case of s, where s is very, very small, we get that v squared is equal to s over 2 minus subleading correction terms. It's demonstrated that the tangential speed of the test particle is approximately independent of the radial coordinate in the galactic halo. But it just depends on this very, very small number s. So this is giving you basically a minimum speed that it rotates around, which is interesting. Consequently, the model through the role of the energy momentum squared term in the field equations for pressureless matter effectively illustrates the presence of dark matter. Now, what's strange here, this I'm not so sure of. It seems like they should have been able to derive this, even if alpha is 0. Right? Because if alpha is 0, you still get S over 2. Which makes me a little bit suspicious of this calculation. There should be an alpha dependence here. Maybe they'll address this. Let's keep reading. Consequently, the model through the role of the energy momentum squared term in the field equations for pressureless matter effectively illustrates the presence of dark matter. The tangential velocity in stable orbits around the galactic halo typically range from 200 to 500 kilometers per second. For a typical, so that's the speed around the galactic halo, 200 to 500 kilometers per second. Is exponential to the b? I don't know what that question is. For a typical spiral galaxy, this corresponds to v squared being order 10 to the minus 6 in c squared units. The v squared comes from e to the b. Right. No, that I understand. Well, that I understand. But the point is that this shouldn't be happening if alpha is 0. Otherwise, like, because if alpha is 0, that just means that you're still getting that. So we'll see. So consequently, by neglecting higher order terms of S, equation 36 reveals that S over 2 is approximately equal to the square of the tangential velocity. No, but alpha, you can take the limit as alpha goes to 0, and this just becomes general relativity. And if alpha is 0, in that limit, you still have this term, right? Which is suspicious. But hopefully they'll address it. Reveals that the S over 2 is approximately equal to the square of the tangential velocity, i.e. S over 2 is v squared. Although this assumption suggests that there we go. Here it is. Although this assumption suggests that the coupling parameter alpha has no significant influence on v, alpha remains a critical parameter for constructing a valid halo model that aligns with observations of galactic halo. I see, okay. Okay, so I'm still suspicious, but we'll see what they have to say. In this section, we explore dark matter signatures resulting from parameterization 14. That's this guy. This is an underlying assumption that they're making. Or rather, it's a parameterization, so it's like an ansatz, something like that, by examining light deflection angles and radio echo delay as detailed in the following subsections. Okay. Oh, this is going to be a mess. Well, let's do it. Okay, so one method to detect the effects of dark matter is through the study of gravitational lensing around and within the halos of galaxies. Specifically, we analyze the light deflection angles where delta phi is defined as follows. So this is the how much light is being deflected by the gravity of some mass. So it's just the what is this? What does this symbol mean? Like phi of r naught. What does that mean? That means that okay. If the light ray starts off a distance r naught away from your galaxy or your halo or whatever, going tangential away from it, then the angle is going to change as it moves out. So the picture is something like this. Let me actually pull up a paint. One sec. Let's pull up paint. Paint. Here we go. I don't know if you can see this. Can you guys see paint? Oh, no, it's horrible. Why can't you see the paint? Yeah, but it's horrible. Why is it like that? Why isn't it letting me show you paint? All right, let me try something else. How about... Let's just try this again. Ah, there we go. Good. Okay, cool. So, we have paint. Okay, so imagine that you have like your big, you know, mass of stuff, right? Let's zoom in a little bit more. You have your big mass of stuff, and you're starting off by, let's use, so orange is going to be our light ray. Let's make this a little bit longer, right? So you're starting off with a light ray that's going out, oops, not, oh, I want a line, please. You're starting off with a light ray that's going this way, right? It's going that way, and your eyeball is over here. This is your eyeball, right? So that light ray, if that mass wasn't there, that light ray would just keep going straight, right? But the mass is there, so instead, what's going to happen is it's going to, we can approximate it as deflecting. What's really going to happen is that it's going to go like this, right? And then it's going to end up, it'll go something like, you know, it'll bend a little bit, and then it'll end up going straight. And so that's the angle that we're measuring, that angle there. And importantly, it's this distance, R0, that they're referring to in the paper. So that's what we're doing there. Now, let's go back to reading. So that's this delta phi. It's this angular deflection difference that they're trying to pick up. So here R0 denotes the region of flat rotation curves. So that's the region where this stuff is happening. Using the geodesic equation 30 for a photon yields, well, so you can just solve the system. Again, they're citing page or reference. Oh, they're just citing Weinberg. Okay. Citing Weinberg's fine. It's a known, it's just a good textbook. Fine. Okay, so they're going to cite Weinberg. Where were we? We were over here somewhere. You can just solve the equation. It's just horrible integral that you have to do. It depends on the space-time curvature. It's going to depend on dr over r. That's your integration measure. It's horrible, but don't worry too much about it. When s is very, very small, only by keeping the first two terms of the metric functions. So again, we have these metric functions, but we can just keep these first two terms. Really, you should probably keep the first three terms, but I guess in this one you only need the first two terms. Oh, where were we? In 26 and 20, yeah, so we're only, oh, no, I'm sorry. We're keeping the first two terms in this. That's fine. Then you can just simplify the integral pretty significantly, I guess. You wind up with these are still horrible expressions, but fine. And so here RD represents the radius, so that's the upper integral here. They're splitting the integral up into two pieces. This represents the radius beyond which the contribution of dark matter diminishes. So they're saying that there's not really any more matter there up to a certain point. Consequently, the first integral corresponds to the dark matter dominated region, while the second integral describes the exterior region of the dark matter halo governed by the Schwarzschild metric. So essentially, if you're a certain distance away, you can just do normal geometry. There's no dark matter there. And so then you can do this thing called the Robertson expansion. I have literally never heard of that. This is also in Weinberg. Okay, so in principle we could go look at it. I think do I have Weinberg? Let me go see if I have Weinberg. I think I have it. Oh, it would be in my textbooks folder. I have Spivak. I have, pretty sure I have Weinberg. No. Oh yes. I do not have Weinberg. I don't have that book, unfortunately. Let's pull it up. Yeah, I just don't have this book. I should get it. Just to have it as a reference. But I'm not going to show you how to do that live, because if we do that, then I might get banned. So we're just going to trust that they're citing Steven Weinberg. He's a brilliant guy, so he's probably getting the calculations right. So then you can apply this Robertson expansion, and you end up with this thing. So we have a fairly, it's like not great, but you have a fairly decent formula for this thing, for this delta phi, this deflection angle. It depends on s. Remember, s is a small parameter, but it's there, right? It's evident that as RD approaches R naught, meaning that's the distance that you start, the effects of dark matter disappear, and the deflection angle is solely due to baryonic matter. Okay. In this specific case, one obtains delta phi is 4gm over R naught, which aligns with the predictions of general relativity. To constrain the model, it's necessary to utilize observational data, including the approximate mass and halo radius of galaxies. In figure 1, the effects of dark matter on the light deflection angle, delta theta for s equals, remember, we had s equals 10 to the minus 6 before. That's what we used to match the galaxy rotation curves in the previous section. So they're going to try a few different values of s, small, as well as for 4 different galaxies listed in table 1 are illustrated. Okay. As shown, increasing the value of s results in a larger light deflection angle. Thus, the parameter s can be interpreted as a representation of the effects of dark matter on the geometry of spacetime. When they say dark matter, what they really mean is like the effect of dark matter that you get from the squared terms. Something like that, I think. So here's 4 galaxies that they're going to use the data from. And this is the deflection angle as a function of, yeah, so as you get more light deflection, the further out, or how do I want to say this? The bigger the dark matter halo. So RD is the dark matter halo size. R naught is like where the baryonic matter size stops. And so you get, so if the dark matter halo is bigger compared to like the size of the baryonic matter, then you get bigger deflection angles. I think I'm interpreting that correctly. Let me make sure. Let's go back and reread. The second integral is the external region dark matter halo governed by Schwarzschild. Yeah, it's actually not super clear what they're doing here, right? Because in principle, they shouldn't be talking about dark matter at all. They're trying to, I assume that they're talking about like effective dark matter or something like that. Yeah, so R naught denotes the region of flat rotation curves. What does that mean? So R naught is the, that's the region of space where the rotation curves are flat. So we're imagining that the light is coming from there. It's very unclear. Maybe it'll add some clarification. But and so RD is again the represents the radius beyond which the contribution of dark matter diminishes. So yeah, so you have some dark matter. There's 2 scales, right? There's the region there's the region where you have flat galaxy rotation curves. That's inside the dark matter halo at R naught. Then you have this second scale, RD. That's where the dark matter stops mattering. No pun intended. And instead we're just left with normal gravity. Volume is really low, sorry about that. It's just because my voice got far away. And so it seems like, yeah, so if you're well inside the halo and the halo's large, then you get more deflection. Okay, that's fine. And this is the deviation from, this should be the deviation, I'm suspicious. How are they getting it down to 0? You should always have deflection. Or is this delta phi? Is this, are they giving us something else? Is this delta phi? They didn't define what phi of R0 is. That's usually how, like the picture that I drew, but it's just not super clear, unfortunately. Okay, anyway, well, we'll put that aside, and we'll make a note, I guess. So let's talk about radar echo delay. One of the key consequences of relativity theory is time dilation, which occurs when light travels near massive bodies. This phenomenon can be observed through the measurement of radar echo delays. Shapiro proposed a method to detect this effect, now recognized as the fourth test of general relativity. It's a cool thing. It's called the Shapiro time delay. Really, really neat. For photons propagating from r equals r1 to r equals r2, with theta being pi over 2, that, again, we're on the equator of our spherically symmetric radius. The elapsed time is expressed as this. So this is the amount of time it takes for a photon to go from point A to point B on the equator. And you can calculate that. Again, you just use the space-time metric. It's a bit messy, but this is found in Weinberg's book, I guess. I've had to derive this before, but it's been a long time. But if it's in the book, just go read the book. By setting R0 equal to by setting R1 equals to R0 in our model, meaning a region where there is flat galactic curves, where R2 is the distant point far from the region surrounding the galaxy, so R2 is now very far away, we can split the integral above into two parts. Again, they're doing the same thing that they did before, splitting it from R0 to RD and RD to R, and then the RD to R part, that's just normal Schwarzschild, and then we have a Shapiro time delay. This is the normal term. This is the normal contribution. This first term is the effect of the region with the flat rotation curves. In the absence of this region, when RD equals R0, where there are no flat rotation curves, we expect the time delay predicted by general relativity, which occurs in the absence of dark matter. Fine. Analysis of the model shows that the free parameter sigma plays no significant role when we assume sigma is much less than RD. Sigma is just a characteristic length scale. To better illustrate the effects of dark matter on radar echo delay, it is useful to investigate equation 43, that's this guy, by fixing the mass and varying RD. In this context, the variation of radar echo delay is plotted for a mass that is 2.2 times, or 220 billion times the mass of the sun, which is a reasonable value for the galactic mass. And then they're picking that R, this is the distance that you want to integrate out to, that's 10 10 times the dark matter halo radius, and they're choosing sigma as 1 because apparently it's independent of sigma. It doesn't actually care so long as sigma is much less than RD, which is fine because yeah, so if they pick RD as 70, 72, 70, or 60 kiloparsecs, the sigma can be 1 and it's fine. Does he read these comments? I do. As shown, increasing the value of RD, which corresponds to more dark matter, so your halo's getting bigger, leads to an increase in the radar echo delay. Let's go look at the plot. So if you make RD bigger, you get more radar echo delay. Yeah, fine, okay. I don't know what units these are in. Probably in natural units, I imagine? Not clear, but okay. And these are for the galaxies that they were talking about. Right, okay, they're going to have some remarks. Hopefully those remarks will actually explain what they were doing. Because it's very unclear. I have some constructive criticism, I think. So dark matter, one of the most enigmatic aspects of astrophysics, challenges the conventional framework of general relativity. With advancements in high-energy physics and particle physics, efforts have been made to interpret dark matter as a form of baryonic or non-baryonic particles. However, these particle-based models have yet to gain substantial support from observational data in particle accelerators. An alternative approach involves exploring modified theories of gravity as a promising framework, wherein dark matter is interpreted as a geometric matter coupling effect. In this work, we have investigated the recently proposed energy momentum squared gravity theory in this context. As discussed, analyzing a model for a dust field in a spherically symmetric and static spacetime close to the framework of general relativity reveals that dark matter can be interpreted as an effect of the squared matter density. Actually, the modified gravity features appears due to the adoption of relation 14, since the parameter alpha enters into the dynamics as a second-order effect, as seen in 36. Additionally, through the study of light deflection angles and radar echo delays, we demonstrate that the model effectively accounts for the presence of significant dark matter in the outer regions of galactic halos. It is important to note that this study focuses on dark matter under weak field conditions, where the gravitational effects of the central object are minimal. Moreover, we constrained our analysis to non-relativistic fluids. Future investigations should extend this work to explore models involving strong gravity or relativistic fluids, which could provide deeper insights into the nature of dark matter. So, they didn't address what I wanted them to address, unfortunately. So, I mean, overall, it's an interesting paper, but I think the trouble or the criticism that I have is that it seems like they could have done this entire derivation in the context of general relativity, completely left out alpha, and they would have gotten the exact same result. Because as they mention in the conclusion, the second order, or the parameter alpha, enters only as a second order effect, and so it's going to be negligible. They never even had to fix alpha to, like, alpha was not some free parameter that they could use to match the data. It's arbitrary. It could be 0 and they would get the same thing. So it's a little bit puzzling. Maybe and maybe it's in the references, but one would think that somebody would have just done this analysis without the stress energy squared term, right? Like, why include it at all if the analysis produces this? Essentially, what they were studying is if you have a central mass and dust around it, can you get dark energy or a dark matter behavior? And their claim is yes. I'm very suspicious of this though. But yeah, so I'd like to see more of that. The calculations are really good though. I appreciate what they did. But it would have been interesting to see what happens if you another thing to see what happens if you like have a significant non-zero alpha. Also, I'm very skeptical of this process where they just kind of ansatz away. Like that's not a given that you can do that. I mean, I guess if you can solve the system, then you can, but like I'm a little bit suspicious. Not to say that it's not a good paper. I may just be not understanding some things. But yeah, I'm just a little suspicious. Anyway, so this paper was called Dark Matter and Energy Momentum Squared Gravity by Fazlollahi, Velten, and Shojaie. So, we're going to call it there. We're going to end the live, and I'll see you tomorrow for Ask a Physicist. So make sure to go watch it, and yeah, I'll see you then. Have a good rest of your day, guys.